So far in this course, we've talked about the analysis phase of systems development and systems analysis and design development. And we've talked about two modeling techniques, which were the use case and domain class model. So we're going to try to extend those a little bit. So let's talk about that. So first, again, we already talked about the use case and the domain class diagrams. Just to review what was a use case, the use case defined the functional requirements of our system, and also talked about the actors or the things, either people or systems that would interface or interact with the system that we're trying to analyze, so the system we're trying to understand. Likewise, the system or business processes we're trying to understand, we could also do a domain class diagram, which showed us all of the things that our system has to keep track of or has to remember. So now that we have these two, we can extend on this. So for the use case, we can develop what are called use case descriptions. It's a more descriptive way to define all of these functional requirements of these use cases. We're going to talk about that, and I'll show you some examples of that. So a use case description, or a fully developed use case description, is going to be much more in-depth than the brief descriptions that we've discussed so far for the use cases. So right now, when we developed our use cases, we used very brief descriptions, but we're going to extend that a little bit in this unit. Once we have those fully developed use cases, we can also develop some activity diagrams. We don't have to have a fully developed to develop an activity diagram, but it certainly is helpful. You'll see why that is. And we can also develop those from the use case. So an activity diagram is basically going to take each use case and show a diagram of all the activities that are required to complete that use case. So that's going to be an activity diagram. So usually you have to have a use case before you can develop an activity diagram. You certainly don't have to develop an activity diagram for all of your use cases, but it does help clarify the particularly complex use cases. So we're going to talk about that. For the domain class diagram, we can take each class of types of objects, so each type of object or each class of things, and we can create a state machine diagram. A state machine shows all of the possible states for a specific instance of an object. So what you do is you take a class. So let's say it's a customer, and we can show all of the states that a customer would transition through. So a customer, or an order, for example, that might be a better example. An order can go through all these different states. It could be an order could be in the created state. It could be in the shipping state. It could be in the completed state. It could be in the back order state. So all these different states that you could have, and you can diagram those different states. So the important thing is an activity diagram is decomposing a use case, where a domain class diagram is decomposing a specific class. You're taking a specific class and showing a diagram of all the different states and how it transitions between those states. So I'm going to show you how to do that in this unit. And also in this unit, we're going to talk about a sequence diagram, which you can develop from the activity and state machine. So you can combine all of these different diagrams into one sort of central diagram, which is the sequence diagram. And I think sequence diagrams are very useful. They give you a lot of insight into how the system works and how people carry out tasks within the system. So you'll see that the sequence diagram can kind of tie all this stuff together. But we can't get to the sequence diagram until we get through our use case, our domain class diagram, and we can decompose those into activity and state machine diagrams, and then we can use those to inform our sequence diagram and to create our sequence diagram. So we're going to talk about those. So just to kind of review these different types of diagrams, we have use case diagrams that define, that show how our use cases and our actors interact with each other, and then we can create a use case description or a fully developed use case description to describe those use cases, and I'm going to show you how we do that. Then we've got activity diagrams, which show you how you carry out those use cases. So what activities are required to complete those? Some activities will be things that our actors do, and some are things that happen inside of our system or inside the automation of our system. And then we have sequence diagrams, which we're going to talk about. And then we have domain classes. We already talked about a domain model class diagram. We already went through how to do that. We can take those classes and decompose those into a state machine diagram. Now, one thing I want to make clear before we move ahead is that these diagrams that we've been talking about, they are UML diagrams, but they're a much more basic version of UML diagrams than we're going to do in the design section of this course. So some of you who have used UML in the field or have some exposure to UML, you may have seen much more in-depth syntax, a lot more in-depth diagrams than we've done so far. What I want to make clear is that in this section of the course, we're discussing analysis. And in the analysis phase of systems analysis and design, we're not designing a system yet. What we're really trying to do in this phase is understand the system that needs to get developed, understand what the current system does, or understand what the customers or the users or the stakeholders' needs are for the new system. We're not going to try to jump into the design yet. And this is very important. I think a lot of students have a tendency to start thinking about design before we fully understand the system that we're designing. And it's a pitfall that in industry is easy to fall into, where you start making a lot of assumptions, based on your own experience and your own interaction. You start to make a lot of assumptions about how you think a system should work, but we haven't gone through this exercise of fully understanding what their actual needs are. So it's important to understand those needs, and these diagrams that we're talking about in this unit and the previous units help you understand all that. But again, what we're not doing yet is we're not actually designing the system. So what we're going to do in this unit is helping us understand the system. When we go into the next section of the course, which begins after, so the next presentation that you're going to see is going to start talking about system design. And that's when we're going to actually start the system design. We're going to use the same diagrams that I've been talking about with the same concepts, but the diagrams are going to get much more detailed, for one thing, and also those diagrams are going to be based off of what we now understand are the system requirements. And how do we understand those requirements? Because of all the analysis that we've done. And a lot of this diagramming is really about helping you understand the system, and the stakeholders know that you understand the system. It's a good way to convey your understanding of the system. And as you're doing these diagrams, not only demonstrate your understanding, but also refine your own understanding of that system. So that's basically what we're talking about here, and I don't want you to think that we're jumping right into design and UML. So use case descriptions. We've already talked about use case descriptions, which in Unit 2 we talked about the brief description, which you would normally provide for almost all of your use cases. You would give some kind of brief description as to what it is, and you might have some basic language in there that talks about the activities in order to complete that use case. So here's an example: create customer account would be the use case, and your brief description could be the user or actor enters new customer account data, the system assigns an account number, creates a customer record, and creates an account record. So that could be just a basic use case description. And for a lot of use cases, developers can see that, and users can see that, and stakeholders can read that, and we all know that we're kind of on the same page. We don't really need to decompose that any further. For other use cases, or more complex use cases, we need a fully developed use case description where we explain the use case in much more depth, much more detail. And this is very important for those complex use cases where it's not obvious how a use case is carried out. So, and I've talked about this before, but a lot of use cases are very obvious, like customer buys product. I mean, I think we all kind of know how a customer would buy a product, and I think a lot of developers and a lot of designers could make some assumptions there, and we'd all be pretty close to what our stakeholders need. But the reason for that is we've all had experience with buying a product. We all have used online systems to purchase products. We all have some familiarity with that before we started designing that system. So it makes a lot more sense, I think, to a lot of us how you would do something like that. But there's a lot of systems that are much more complex that you don't always know exactly what these activities and steps are to complete a use case. They're a little more abstract. They're a little bit more specific to a specific business process and a specific type of business that maybe isn't in the general understanding of most people. So, for example, in the insurance industry or the healthcare industry or manufacturing, things that a lot of us, unless you work in those fields, you don't deal with those workflows every day, so you don't always know exactly what people expect. So those types of workflows or use cases or functional requirements, we're going to want a more granular description of those. And that's what our fully developed use case description is for. Now, of course, in the example, I'm going to give you a fully developed use case description for something that might be pretty obvious. But the reason I do that, and I think I've talked about this before, is it helps us all understand the syntax and the rules for these diagrams. So I'm really trying to convey how you develop these diagrams and how you develop these descriptions, in the correct way. And I think a good way to do that is to use something that we all know. But of course, in your projects and in your running case that you do for this course, you're going to be diagramming things, and you're going to be doing this for things that are not well understood, that are a little less obvious, which is good. That's what we want to do, and it'll help demonstrate your understanding of that stuff. So in a fully developed use case description, you'll usually have a name for the use case, which we had in the basic one. You'll have a scenario if it's needed, if you need that to clarify things. You'll have the event that triggers the use case, a brief description, which again, we should already have a brief description. We already know the actors, but we're going to list who the actors are. It could be more than one actor that interacts with the use case. Any other related use cases? I talked about that includes relationship in Unit 2. So you would list those if it's an includes relationship. Who are the stakeholders that stand to benefit from this use case? We'll also list the preconditions, so the things that have to be true before the use case can commence. And when the use case is completed, the postconditions are what should have been completed at the end of the use case. A flow of activities, I'll show you an example of that, and any exceptions. So things that happen that would indicate that the use case failed to meet its goal. So these are all the parts and it's a pretty lengthy document usually that you would create from a fully developed use case description. Here's an example of one. It's a little bit too small for me to show you in one document, so we'll break it up into two parts. I'll show you the top part first. We have our use case description. In this case, it's create customer account. Create online customer account is the scenario. The triggering event. So what triggers this? Well, the customer wants to set up an account. That's the trigger. I would also add to the trigger maybe something about the customer creates a shopping cart or adds things to a shopping cart, wants to check out, but they can't because they have to have an account first. So that would be another example of a trigger. A brief description, which we already had from before, so a brief description of the use case. Who the actor is, in this case, the customer is the actor. The related use cases, so in this case, the checkout shopping cart is a related use case, which I just discussed. The customer might have a shopping cart, and that shopping cart is related to this use case. The stakeholders, so who are the people that benefit from this? Accounting, marketing, sales. The preconditions, so the things that have to be true prior to this use case, and what we can expect to see after the use case is completed in the post condition. So, for example, the customer must be created and saved. We have to have an address. We have to have a credit or a debit card number. It has to be a valid credit and debit card number, things like that. So those are our post conditions. The next part is our flow of activities, which is arguably one of the more important parts. This is really going to clarify this use case. It's going to list all of the steps that both the actor and the system are going to have to take in order to complete the use case. So on the left side, you can see all the things that the actor is doing. And on the right-hand side, all the things that our automated system is doing behind the scenes. So for example, our customer indicates they have a desire to create an account. Whatever mechanism that is in the user interface, they trigger this by saying, I'd like to create an account. The system is going to create the new customer. It's going to prompt the customer for their address. Once that prompt happens, now the customer's responsibility to enter the address. Once the address is entered, it's going to get created, and then it's going to ask for the debit and credit card. Now the customer has to enter the debit and credit card information, and then when that's completed, then the system is going to create the account, validate the debit or credit card, associate all that stuff to the customer record, and return the valid account details to something. It could be some other automated process. It could be the customer, whatever it is. So that is all of the activities that it takes to complete this use case. Now, try to remember those activities. So take a look at this slide and look at the actor, look at the systems, and try to remember all of these different steps, because we're going to look at this in just a few minutes when we look at an activity diagram. Finally, the last thing is the exception conditions. So these are the things that if it doesn't get completed, that we can say this use case failed. This use case cannot be said to have been completed if any of these exception conditions happen. So that's basically a fully developed use case description. So lots of stuff in there. Let's talk a little bit more in detail about each one of those sections. We have our use case name, which, as we already talked about in Unit 2, is a verb noun label. So does something, basically. The scenario, if it's needed, you don't always have to have a scenario, but if it's needed, you can have a scenario if it offers some clarity to the use case. You'll have some kind of a triggering event. So something that happened that caused this event to kick off. And again, that's going to be based on our event decomposition technique, which we talked about in Unit 2. So there was the user goal technique and the event decomposition technique. So the triggering event we would have identified in that decomposition technique. A brief description, which we already talked about again in Unit 2. The actors, which are the things or the people or the systems that would interact with our system. Anything external to our system that has some that would kick off this functional requirement or this use case. Then we have the related use cases, which we talked about. So if one case invokes or includes another, that would be a related use case. So either if our use case is invoked by another use case, or if this use case can invoke another use case, those would be listed in the related use cases. The stakeholders are the people that stand to benefit or have some interest in this use case. The preconditions are what must be true before the use case begins. And the post-conditions, likewise, are the things that have to be true after the use case begins. The interesting thing about post-conditions is it tells us all of the things that our use case should have accomplished. So that's something that we can use later on for our testing. And we're going to talk about testing later on in this course. But when we develop our test plan, our use cases are a really good resource to figure out what we need to test. So if we know that when a use case is completed that certain things should be true, that's something we could test for later on. So it's definitely a good thing to test to have those post conditions, and we can reference those later when we do our test plans. The flow of activities we're going to use to create an activity diagram later on, but it's all of the activities between the actor and the system. So that's the flow of activities in a use case. And finally, the exception conditions, which just like our post conditions can be used for our testing. So we can test those exception conditions. What happens if I put an invalid debit card into the system? Is it going to correctly catch that exception? So that's something we could list. So let's take a look at activity diagrams, which once we complete that use case, fully developed use case description, we can create an activity diagram. You don't always have to have a fully developed use case description for an activity diagram, but it's certainly a good idea to do so in a complete and detailed systems analysis. So an activity diagram is going to show us in a diagram the activities in order to complete a use case. And sometimes it can offer some clarity on the process to complete a use case. So I'll give you the syntax first. We have what we call swim lanes. We're going to talk about swim lanes with sequence diagrams as well. In our analysis diagram, so when we do an analysis, in most cases, we only have two swim lanes, the actor that we're working with and the system that actor is interacting with, which is our overall system. This is all contextual level, so we're not really decomposing this much further at the analysis phase. You'll see that when we get to the design phase, these diagrams get much more detailed with additional swim lanes. But for right now, we're only worried about the actor and the system. So we have an actor. There's always an initial state or a start of the activity. And then we have the actions, which we usually put in some kind of an oval or a circle. So you have your actions. And you can also have decisions. So yes, no. So if this is true, we're going to go do this. But if this other thing is true, we're going to go do something else. So you'll have a decision. And they can lead into additional activities. You can have a split, which splits into other activities that can run concurrently. And when those all finish, they could go to a join when they join together again. And finally, at some point, you've got a final state. So we have an initial, some actions, decisions, maybe a split or a join, and then a final state once we're completed the activity. So this is the syntax for an activity diagram. Let's take a look at an actual activity diagram. So we've got our customer and our system. So the customer is the actor, and the system, of course, is our system. If you remember that from that fully developed use case description that we looked at, the first thing that happened is the customer requested an account. Then the system created a customer. Once the customer was created, our system, the customer had to enter an address. Once the address was entered, the system created the address. Then it prompted for a credit card information, which the customer had to enter. Then that credit card information was created. We verified the credit or debit card, and then we return the account details, and we're done. So that's a basic activity diagram. Again, this is very basic. They could be much more complicated in the real world with more complex things that aren't as obvious. But this is basically what an activity diagram would look like. And again, they give us a little more clarity on how a use case is accomplished. or what steps and activities both the system and the actor take in order to complete that use case. So now that we know what an activity diagram is, which decomposed, so just to clarify, that activity diagram decomposed our use case. Now we're going to talk about decomposing the class diagram, or our domain model, our domain class diagram, which again is at a very high level. This is all in our analysis phase. So how do we decompose that stuff? We use a state machine diagram to do that. So a state machine is a UML diagram that shows the life of an object in states and transitions. So a specific instance of an object, so a thing that we have to keep track of in our system, or a class, which describes a type of thing that we have to keep track of, can have different states. So it can have these different states, and it has to transition between these different states, and that's what we're trying to show in a state machine diagram. A state is a condition during an object's life when it satisfies some criteria or performs some action or waits for an event. So any object can have a state. I like to use the example of Lassie. Dog is our class. An instance of dog could be Lassie. So if we're diagramming states of Lassie, Lassie could have a state of wagging tail and chewing bone. Lassie could transition to a state of hearing Timmy scream from the well, and then it could have a state of running to go get help, and then it could have a state of laying down and taking a nap or something like that. But certainly Lassie would not be in a state of laying down and taking a nap before he saves Timmy from the well. Although I guess he could, but then we wouldn't have Lassie and Timmy and all that stuff. So you can have all these different states. So we could talk about the different states and how they would transition, how an object transitions from one state to another. And again, this is just a technique to decompose our class diagram. So a transition is the movement of an object from one state to another state. And an action expression is a description of the activities performed as part of that transition. You're going to see an example of this. A pseudo-state is a starting point of a state machine diagram, or the ending state. That's a pseudo-state. It's not a real state, but we have to start somewhere. So that's a pseudo-state. And the original origin state is the first state of the object. Before, when an object is created, it has an origin state, and then it can transition to other states from that origin state. And a destination state is the state to which an object moves after a transition. So an origin state is before a transition, and a destination state is after the transition. You have guard conditions. A guard condition is a true-false test to see whether a transition can fire. So sometimes before we can transition into a state, we have to check to make sure that something is true or false. So that's a guard condition, and I'll show you an example of that in our sample. Let's first take a look at the syntax of creating a state machine. So for example, if I were drawing a state machine diagram for a printer, right? So let's think about a printer. From a very high level, a printer can have basically two states. There's two primary states that our printer can have. It can either be off or it can be on. And if the off button is pushed, it transitions to the off position. How do we transition to the on position? Because the on button is pushed. But here's an example of a guard condition. If we're in a state of off and somebody hits the on button, that's our transition, hitting the on button, we can have a guard condition that checks, is the cover closed? And if the cover is not closed, we don't transition to on. If the cover is open, we will not transition to on. If the cover is closed, then we will transition to the on phase. And the action that we take as we transition to on might be a self-test. So the printer might do a self-test before it gets to the on phase. Likewise, and then finally, of course, if you hit the off button, we're going to transition right back to the off phase. The dot that you see on the front is a pseudo state. It's not an actual state. It's the beginning of the state machine. It denotes where we start from. So usually when the object is created, it's created with a state of off. And then we can turn it on by pushing the on button. And we can turn it off by pushing the off button. And likewise, we can keep going around and around and around. So we have the beginning, which is the dot. We have the state, which indicates the state of being of the object. So this particular object has two states. Make very clear here that a state machine diagram is not showing us different objects. It's all the states of a single object. So you would normally not have in a state machine diagram different objects. It's all one class. So a state machine is always representing all the states of an object in one class. So those boxes are not classes. Those are states of a single class. We have the transition, which moves the object from the origin state to the destination state. So in this case, the origin state is on, the destination state is off. I can tell because the arrow is pointing to off. And again, that arrow is important. A lot of students, make these diagrams sometimes and forget the arrows, but that arrow is important. With the printer, we all know that we would go from on to off and from off to on. But again, in less obvious systems where it's a much more complex workflow, we don't always know that. So it's important to for these little things like the arrows to be pointing in the right direction or to even have the arrow. On the top, we have a much more complex transition. We have the actual transition, a guard condition, and we have an action expression. So it's a little more complicated for going from off to on, but in a typical transition, we might have all these things. So that is a basic syntax of a state machine diagram. I'm going to talk about some other things we can do with a state machine diagram. So let's shrink this. So there's our basic state machine. We have off and on, and I already talked about the transitions between off and on, so we'll hide those for now. But I can take that on position, and I can decompose that even further. So when the printer is on, it can have multiple states while it's on. So our printer has an off state and an on state. But when it's on, it can have some composite states. So when it's on, it could be idling, or it could be when we're printing a document, it's working. So it loads and prints the sheets. So we could be an idle, and then when we print, which is our transition, and by the way, document is something that is passed to the next state, we're working. And then when we're done working, when we're finished printing, so the guard condition is if we are finished. So there's no more documents to print, then we transition back to the idle state. And then we transition back to working the next time somebody prints a document. So we decomposed the on position. So if I were to redraw this state diagram, the state machine diagram, I would have an off outside this box that you see on the main part of the screen. And inside that on position, I would have additional states within that. And you can even decompose this even further. You can have composite states even within those if you wanted to, depending on what level of granularity you need to go to in the diagram, which again is very subjective. That's a judgment call as to how deep you need to go in these diagrams. So another thing we could have is concurrent paths. So here's that same on state, but within the on state, we already talked about being idle and working, but we can also have a concurrent state for the printer being empty. So usually when you buy a printer, our initial state is empty. You put paper in. So with the fill action, or the fill, we transition to being full by filling the magazine. And then when we print a bunch of stuff, eventually it's going to be low. So the low message transitions us to being in a state of being low on paper. And in order to get back to full, we can fill again and get back to full. Or if we keep printing and we fail to fill it, eventually we get back to empty. So we have two states. We have multiple concurrent states. We can be both idle and empty at the same time. We could be working and be full or low at the same time. But we can't be working while we're empty. So those are concurrent paths. And again, these are, states that can exist at the same time within another state. So the master state is on. The printer is on, but it can have all of these other states while it's on. So steps for developing the state machine diagram. We have 8 steps. Step number 1. Oh, sorry. Let me go back here. Step number 1, review the class diagram and select classes that might require state machine diagrams. Step number 2 is we're going to make a list of status conditions that you can identify. Next, we begin building a diagram by identifying transitions that can cause the object to leave the identified state. Then we're going to sequence those states in the correct order. So there's usually some kind of an order to these states. You wouldn't go from being full to being low to being empty with the printer. The printer would usually start as empty, and then it would be full, and then eventually it would be low, and then we would either go back to full or we would go to empty because nobody filled it. We would review the paths and look for independent concurrent paths, which we just did in the example. And then we look for additional transitions and tests in both directions. Expand each transition with appropriate message event, guard condition, and action expression. We want to try to think about not just what's the transition, but but what are the guard conditions that we want to make sure are true before we transition, and any actions that we're also going to take during that transition. The last step is to review and test the state machine diagram for the class. We're going to make sure that the states are really states for that object in the class. So if we take an instance of a class, if we make an instance of a specific object in that class, we're going to check to make sure that the states are all true for a specific instance of that object. We're going to follow the life cycle of an object coming into existence and being deleted and make sure that we can transition it through those states as just an exercise. We're going to be sure that the diagram covers all exception conditions and look again for concurrent paths and composite states. Where could we get those exception conditions? We could look at our fully developed use case description, which we talked about earlier. So those are the basics of a state machine diagram, and you'll see some examples in your textbook for those. So I'll give you some examples here too. If we take, for example, the sale item, the class sale item from our domain class states for the RMO case, we have 4 states: newly added items, ready to ship, on back order, and shipped for a sale item. So these are items that have been sold. So it's either newly added to a order, it's ready to ship for an order, or it's on back order, so we're waiting for more of them, or it's already been shipped. And that's it. So if I were to draw a very basic state machine diagram for that, it would look like this. So we have on back order, the item has arrived, it's ready to ship, and then it gets shipped. If it's newly added, if it's ready to ship, then it gets shipped. Otherwise, it's on back order. Now you can see there's a little bit of an issue with that diagram. It doesn't quite show you those state transitions very accurately. So we don't know that relationship between on back order. Is there a way to go from newly added to ready to ship to on back order? There should be a way to go to back on back order. So that's missing, and that would become clear when I look at a state machine diagram. It wasn't quite clear in the table, but now I can see that I'm missing a transition there. So we could redraw this a little bit and make it more accurate. So there is a slightly more accurate version of this of the state machine diagram. So now, if when we add an item, which is so we go from a pseudo state of start to add an item. Now we have a newly added item. When it gets created, it's newly added. It can either be marked as back ordered and be on back order, or it can be finished adding and go right to ready to ship. So it can go in either direction. And the guard condition could help us. We could develop a guard condition to help us decide which direction it should go. On back order, so if the item has arrived, it's ready to ship. If it's ready to ship but marked as back ordered, it's going to transition to on back order, which is what we identified before as being an issue. Once it's ready to ship, then we ship the item, and at that point it's shipped, and we archive it, and we destroy that object. So the object is complete. So that's the entire life cycle of that object and all the states that it can have as it goes through those the life cycle. Another example is the sale item object. So this one's a little bit more complicated. So this might be a first draft on this. When we take this table that we brainstorm of all the different states and the exit transition of those states, we can draw that out. And again, we're going to identify some things that maybe need some clarity or to make it more consistent. And then we might have a final version of that state machine that looks like this. And again, this is from the textbook. So you can take a look at this in the textbook. Now we're going to talk about sequence diagrams. So we sort of tie everything together. At this point in the analysis, we would have finished the use case diagram. We did some fully developed use case descriptions. We did an activity diagram for those that needed a little bit more clarity, that are complex activities. Then we went over to our domain model, our class diagram basically, and we decomposed that into states, into state machine diagrams. Now we have a much better understanding of our system, and we can start to build a sequence diagram. So let's take a look at a sequence diagram. A UML sequence diagram is how we show the sequence of events and how all of the different objects communicate with one another inside the system. And also our use cases, our actors rather, how they interact with the system. Now, in a analysis system sequence diagram in the analysis phase, we're only looking at the entire system. So we're not going to break this down we're not going to decompose this much further than just the system and the actors. That's really as far as we need to go in a sequence diagram at this level. But one of the things that I want to talk about real quick is that in industry, what I've noticed is a lot of times, we're going to talk about sequence diagrams in much more detail in the design phase. And a design sequence diagram is a little different than our system sequence diagram. Our system sequence diagram isn't as stringent. It's not, we don't have to comply with the rules as stringently as we do in a system design. System design sequence diagram is all about developing a program at some point, where right now we're just trying to understand what that program needs to do. So one of the common things that I'll see with a system sequence diagram is not only diagramming how actors interface with our system, but remember, our actors could be lots of different types of things. Actors could be people, they could be other systems. So in complex systems that involve lots of different systems interacting with another system, I'll see sequence diagrams that show how all these different systems talk to each other in order to accomplish a single task. I work in healthcare a lot, and in healthcare we've got all these disparate systems in a hospital that all have to work together to accomplish a goal. So when a patient is admitted to the hospital, you've got one system that's handling their lab work, another system handling their radiology work, their x-rays and things like that, another system handling feeding the patient, providing the food. You've got other systems that are handling the billing, other systems handling the doctor's notes, and all of these systems have to work together. So it can be a rather complex interaction between all these systems. So a system level sequence diagram helps us understand how all those systems work together. Now I'm going to show you some more basic examples in this presentation, but I just wanted to give you some sense of how we use these in industry. So it only shows actors and our system, the system itself as one object. And the one object represents our complete system. So we don't decompose our system in a system level sequence diagram. We're just saying, here's all the stuff that's happening in our system, and here are the actors that are going to interface with it. This is what they're expecting to send into the system. This is what the system's going to send back in order to accomplish different tasks. So it shows input and output messaging requirements for a specific use case. So we usually have an actor, the system, and an object lifeline, and then messages that are flowing back and forth between the actor and the system. And you'll see that on the lifeline. So I'll show you what this looks like. We're going to look at the syntax for this. So here is the basic syntax of a system sequence diagram. You can see in this case I've got a clerk, which is my actor on the left-hand side. And then there's a line that's drawn down. So let's look at these different parts. So we have the actor, which is interacting with the system. We have an object representing the automated system. So there's our system, basically, that the actor is going to interface with or interact with. Then we have the lifeline, which shows time. So that lifeline is sort of an extension of the object over time. So it shows it's the lifeline. So as you read down, this is the passage of time as we go down that lifeline. And you'll hear some people refer to these diagrams as swim lanes, because they look like swim lanes. But that's the object lifeline that you see that line going down. Then we've got the message. So there's always an input message. And then we have a return value or an output message going back to our actor. And finally, on the right-hand side, off to the side, you've got an optional note that can explain something in a diagram. So if something needs some clarity or it's not obvious, you can have a explanation in an optional note. And that's the syntax for drawing a note with that little chopped off corner on the upper right-hand side. So let's take a look at the notation for the messages. So I showed you some messages there, some basic rules for message notation. We're going to talk about this in more detail again in the design phase, but just to give you a little taste of this, the asterisk indicates a repeating or looping message. We'll show you an example of that. Brackets indicate true, false. So that's like a guard condition from our state machine. So it's a test for the message, only for that message. So if it evaluates true, the message is sent. If it evaluates the false, then the message is not sent. A message name is the description of the message service. It's omitted on dash line return messages, which only show the return data parameter. So we don't have to have that on the return, but we'll have a message name on the input message. The return message, it's implied, is a response to that message. The parameter list, usually with parentheses on the initiating message, but no parentheses needed on the output because usually it's only parameters being sent back, shows the data that are passed with the message. So when we send the message in, we could have a message that says do something, but with no parameters. Or we could have a message that says do something, and here's the parameters you need to do it, or arguments if in the parlance of programmers. So, and then we have a return value on the same line as the message requires a := sign, so it's an alternate syntax for the return value. So our return value can either be a dotted line showing the return, or we can indicate that we expect to get a return to that message with the equal sign. So we'll see an example of that in just a few minutes. Let's take a look at an example of a sequence diagram, but this time I'm going to show you a loop frame. So I talked about those different messages. That first diagram I showed you is a very basic example, and a lot of diagrams just have those basics, but you might have conditions that have to repeat over time. Let's take a look at an example of that. So our clerk needs to repeat something. For example, we're adding items to an order. So we normally don't add the items all in one move. We have to select each item one at a time and add it to the order. So that would be a looping condition. So one way to show that is with a frame. We can do what's called a loop frame. So in the we have a test condition for repeatability in that little note you see up at the top. So we always have to have the condition. In this case, the condition is for all items. So for all the items that have to be ordered, we're going to loop for each one of those items that we have. And until we have no more items, we're going to keep looping. So each time we still have an item to be added, we're going to add the item, and we're going to send the item ID and the quantity to the system. The system is then going to return a description and a price. So this is one way that you could diagram the looping condition for adding items. Another alternative method is we could do this with a simpler notation. Well, I shouldn't say simpler. With less notation, but I guess it could be read by some people to be a little bit more complex. But the asterisk on the front means it's looping. So we're saying loop while there is another item. So we're going to loop. So we have the loop. There's the guard condition. It tells us what we're looping for. And then what we're going to send, in this case, the return is going to be the description and the price. But we are going to send, so add item is the message that we're going to send, which is going to be the item ID and the quantity. And notice we've got that equal sign in there. On the left side of the equal sign is the description price that comes back. But on the right side of that equal sign is what we're sending, the message that we're sending to the system. In this case, the add item with the item ID and the quantity. So that's the syntax to do a loop condition without having to do a frame. So you can do it without a frame, or you can do it with the loop frame, whichever you think is more clear in your diagram. So that's one syntax for a sequence diagram. Another thing you have to be aware of is an if frame or an optional frame. So you have an opt frame or optional, which is sort of like an if condition. So here's an example of an if frame. We have a clerk that if an accessory is selected, so this interaction with the system only happens when there's an accessory that's been selected. If the accessory was selected, we're going to add the accessory, and we're going to pass it whatever the accessory is, and then it's going to pass us back the accessory details. And again, I could do all of that with one, I could do this without doing the frame. So we could just use a guard condition and do this without a frame. So you can do it either way. So that is an example of if you had some if logic or conditional. I would say that this is conditional, right? So this is sort of a conditional frame, but the official name is optional frame. Another one is an if else, right? So sometimes you can have a conditional that if it's true, otherwise if it's not true, you're going to do something else. And these can be more than just one or two things. You can have if this is true, do something, else if this is true, do something, else if this is true, do something, and then finally an else if none of this is true, then do this, sort of last resort. And anybody who's done some programming, you've probably worked with these conditional logic before. This is called an alt frame. So if it's an if else, it's an alt frame. So our guard condition in this case is the clerk is going to add sales tax if it's a taxable item. So if we have an item that's taxable, we are going to add sales tax with a location code because sales tax is going to be different depending on the location. Then our system is going to return the amount for the sales tax. So that is the first part. Then we have a line that separates to our next guard condition. So our next guard condition is else. So else, if it's not taxable, in other words, if it's not a taxable item, we're going to add tax exempt code and then get back tax exempt detail. Now, we could just as easily, instead of having else, we could have an additional. So for example, I could say the first condition could be if it's a taxable item, then add sales tax. The next condition could be if the customer is tax exempt, then we do add tax exempt code for customer. Else, then we just add a tax exempt code for the item. So you can have different conditions here. You could keep going with these additional conditions in an alt frame. So that's an example of an alt frame. So your steps to developing a sequence diagram. First, you're going to identify the input message. So use your key use case flow of activities in your activity diagram to determine what those input messages are going to look like. Describe the message from the external actor to the system using the message notation that we talked about. It's going to be a verb noun, so what the system is asked to do, and consider the parameters that the system will need. Then we're going to look at the identify any special conditions on input messages, so those guard conditions. If it's a frame or if some kind of iteration or an opt or an alt frame, so do we have to check some kind of condition with some conditional logic? We're going to identify and add any output or return values that we're going to send back to our actor. So on the message itself, we could do it with that equal sign that I talked about, or we can do a return, an explicit return with the dashed line that I talked about. So 2 ways we can do those returns. And whichever one you think is clearer, you could use. So whichever one you think would make more sense in your diagrams. Let's take a look at an example of these diagrams. So here is an example of a simple sequence diagram. We've got our customer. They create a new customer. They pass the name, phone, and email. Then our system returns back the customer ID, the name, the phone, and the email. Then we can add an address. Now notice the address is a looping condition. So we loop with address details, we loop by entering an address, and it returns the address details. So we did all of that with one line instead of doing an explicit return. We enter credit card information, and then the credit card information details can be returned. So here's a simple example of a sequence diagram, and also from your book. So here's another example from your textbook. Again, this one's a little bit more complicated. We have our shipping clerk, which gets the next sale. Then they get the customer's address, the sale, and the item information. Then they're going to get the shipper information. Next, they're going to loop through shipping the items. So for each item in the order, they're going to ship each item until they're done. And then they're going to loop through the back-ordered items. So they're going to record the back order and get the back order confirmation. Then they're going to get the shipping label, attach and they're going to request to get a shipping label with the package size and the weight, right? So they're going to provide the package size and the weight. Hopefully the system already has all the address and all that stuff. They get back the label, and at that point the system is done. Our shipping clerk is going to go attach that label to a box and hand it to the UPS guy. So that's again a basic example of a sequence diagram, at least a system sequence diagram. As I said before, when we do our system design, these sequence diagrams are going to get a lot more complicated because we're going to try to show the messages between lots of different objects. In other words, in order to complete this task, it's going to require the interaction between different classes in order to complete this class. So eventually we're going to show these sequence diagrams, how the system itself is completing all this stuff. But this is our first step to really understand how the actors are going to interface with the system. And then later on, we'll design the system. So that's it. That's all I have for you on extending the requirements modeling. If you have any questions, please reach out to me. Thank you.